This is a high-low circuit. Such a circuit would be used to achieve high speed or rapid advance at low pressure, followed by slow speed and high force. A good example of a high-low system would be a press where the ram would rapidly advance up to the workpiece. At that time, the pressure starts to build. The flow from the high-volume pump is diverted to the tank. The low-volume pump would produce the little flow needed to continue moving the ram into the workpiece. The pressure will continue to rise until it reaches the relief valve setting. When the directional control valve is reversed, the pressure drops and the unloading valve closes. The cylinder would retract at a rapid speed. Now let's examine more closely the components that make up this system. First, the unloading valve. This valve has been set at 500 psi. When the system pressure reaches 500 psi, this valve will open and allow the flow from the high-volume pump to go back to the tank at minimal pressure. Next, we will look at the function of the check valve. When the system pressure is less than the unloading valve setting, flow from the high-volume pump flows through the check valve to combine with the flow from the low-volume pump. After the unloading valve opens, this check valve closes so that the flow from the low-volume pump won't flow to the unloading valve. Now, let's take a look at the high-low pump group. This is a double pump. These pumps have a common inlet and separate outlets. During low-pressure rapid advance, both pump flows are combined. When the unloading valve opens, the large pump's flow returns to the tank, and the small pump's flow is used to do the work. Finally, we will look at the system pressure relief valve. This valve limits the maximum system pressure. Notice the schematic shows the pressure at which the valve should be set. Now, watch as these components work. In our circuit, the cylinder has a weight that would cause it to free fall or drop at an uncontrolled rate. A counterbalance valve is placed in the rod end port of the cylinder to apply back pressure. The back pressure is the result of the load trying to force the fluid out of the cylinder and through the counterbalance valve, which is closed. The counterbalance valve has to be set slightly above the load-induced pressure. When shifted, the directional control valve applies pressure on the cylinder piston. This, in turn, increases the back pressure, causing the counterbalance valve to open, allowing the cylinder to lower the load at a controlled rate. Now let's examine more closely the components that make up this system. First, we'll look at the offline or kidney loop filter circuit. This circuit consists of a pump motor group, a filter, and an air-to-oil heat exchanger. The pump draws hydraulic fluid from the reservoir, passing the fluid through a filter and an air-to-oil heat exchanger. This circuit usually runs continually to keep the hydraulic fluid clean and cool. Next is the pressure-compensated pump. The pressure-compensated pump de-strokes when the directional control valve is centered. At this time, there is pressure being maintained between the pump and directional control valve, but no flow. When the directional control valve is shifted, the pump goes on stroke, providing flow for the circuit. Next, we have the directional control valve. This is a 3-position, 4-way valve with a float center. This valve, when centered, will block flow from the pump so that pressure will build and de-stroke the pump. Both work ports are routed back to the tank, so there is no pressure in the work port lines, except between the rod end of the cylinder and the counterbalance valve. Now, we look at the counterbalance valve. The counterbalance valve maintains back pressure on the rod side of the cylinder so that the cylinder brings the load down at a controlled rate of speed. The check valve is used to lock and hold the load on this cylinder when the directional control valve is centered. Now, let's watch the system work again and see how each component operates.